Hello, and still good morning. Today we will start a new chapter. As I told you, we will start vector spaces. This chapter is very, very important. It connects a lot of things together. It's major thing in understanding what's gonna come next, especially in linear algebra. This is one of the beautiful chapters. It needs you to understand it carefully, step by step, to know the meaning. And we will have a lot of problems to make everything easier for you, inshallah. It's another flavor, as I told you, about the just a little bit twist than matrices and so on. We finished matrices and we used matrices in the solutions of a linear system of equation, either to hunt the echelon form or to get a reduced echelon form and the related cases in a solution of the system of equations. In the previous lecture, we already introduced another method for solving a system of equation, which is Kramer method. Also, we went in details about the propositions of the determinants, how to evaluate a 2 by 2, 3 by 3, even more than that, how to simplify a little bit a form of a determinant, then going to evaluation. It's really very important. Now we will go to vector spaces. The understanding of vector spaces is really major for linear maps. And all will be connected in eigenvalues and eigenvectors. Everything that we have. Matrices, everything. Then we will have the linear product, cross product, which is somewhat related between the vectors and matrices and the vector spaces and so on. And then finally we will go to an introduction in analytic geometry in 2-dimension and mainly in 3-dimension for the straight line and the plane. That's what that is. Okay, let's start first with this. Of course, I will send you this slides or this bunch of slides. Those are some of the symbols that's used and the abbreviations that we usually use in writing expressions in mathematics, and it's measured to now. This arrow, this up arrow, it's a caret and it represents and. Dot, it represents an and also. Plus, it's plus and it means x plus, values of x plus y, and also exactly the same. The vertical line, this is the small vertical line stands for or, so it means x or y. Okay, the arrow that's head going down, okay, this small arrow, it means or also, so I can write x or v in this way. Remark that I have x and v if it is upward, okay. You will have the exclamation mark, which means it's not negation. If it was written on the other side, it means a factorial and so on. Okay, this symbol, it stands for equivalent. Also, like this one, it means equivalence. Of course, you know this, which implies this belongs to, this doesn't belong to. That's for every, which is the A reversed, okay, with a sign inside it, which means for all. Also, we have E, the reversed E with just only a dash. It means there doesn't exist. The same symbol, but without the dash, it means there exists. Of course, this is because of sense. I thought to gather these symbols for you to make your life easier reading or writing something. Okay, Faisal? Okay, let's go about the definition of the vector space. I want you from the beginning to understand what we meant by a vector space or what we resemble in general in this part. A vector space is a set of objects. It's better to call it this way. It's a set of objects called vectors together with two operations. Those two operations are the addition. So it's a vector addition. You can add two vectors and get another vector belongs to this set. And the second major condition, it has a scalar multiplication. You can multiply a vector by a number and get another vector in this set. These operations must satisfy some basic rules like the associativity, the distributivity, the existence of a zero and vectors, and simply it can be defined as the following. A vector space is a collection of vectors. The vectors, it's not just only the vector with a direction. A vector, it stands for any group of objects or operations. So any bunch of operations or objects, it's really very easy to imagine it as a vector, either in 2 dimension or in 3 dimension. But to be a vector space, this collection of vectors or this collection of objects, to be called a vector space, 2 major conditions must apply. If you have 2 vectors and added them together, the result should belong to the same vector space or to the same group. Okay? The multiplication of any vector, also the result should exist in this set that we are talking about. So a vector space is a collection of vectors where you can add them and scale them. Remember, scaling a vector, it means multiplying it by a number. So this is how we scale stuff. We multiply any number by a ratio or something. So scaling, this is from where it comes the meaning of scaling. So if I have a vector and multiplied by 2, it means all the components of this vector will be multiplied in 2. If I have a vector and multiplied by half, so all the components of this vector will be divided by 2, and so on. Okay. As I told you, add them and scale them by numbers, and the results still belong to the same collection. The main rules and the axioms of vector space. Suppose we have a vector space V. Suppose I have a collection, a set of vectors, and I will call them the vector space V. How to be sure that this vector space really exists? Okay. Numbers like real numbers belongs to R with vectors U, V, and W. So U, V, and W are images or are objects that belongs to the vector space V. And their scalars, numbers A and B, those are 2 numbers. The following operations must exist. The first operation is addition. As I told you from the previous slide, in order to call V a vector space, 2 operations must exist. The addition of any 2 objects inside V should result in a vector that belongs to V. And also, any vector belongs to V if you multiply by a number, the result should exist in V. This has a consequence. This is the propositions related to the addition rule in general, Ms. Sulay. If I have the closure, what we mean about closure and the addition? The closure and the addition, it means if you get the sum of any 2 vectors, the result will belong to V. The commutativity, what we mean about commutativity, if you replace U and V to be V and U, the result also will be the same. And the result will exist in V. Associativity, which means if you have 3 vectors, I can add 2 of them, then having the result and add on the third one. Or adding the third and the second one on each other, and then adding the result to the first. This is what we mean about associativity. The zero vector, which means a vector from the same dimension with all elements equal to 0 and also should exist in the V. Those are all of them conditions related to the addition process in any 2 vectors. Number 4, additive inverse. If I have a vector W, I should have a vector negative W. If I add them together, the result will be 0. And the 0 belongs to the V. This is the first condition for V to be a vector space. The second condition is scalar multiplication. What we mean about scalar multiplication, it means if I have U and scale it with a number, the result will belong to V. And the distributivity, if I have a constant and distributed it on the addition of 2 vectors, it will be distributed in the first and the second. The associativity of a scalar or the distributivity over a scalar addition, if you have 2 numbers added together and multiplied by a vector, it's exactly the same like adding the multiple of the first and the multiple of the second, and so on. Also, the identity existence of a scalar, if I have a u vector, Farid, and multiplied by 1, it's going to be the same vector. So bottom line, what's a vector space? It's a collection of a bunch of vectors or a bunch of objects or operations. The simplest thing to imagine it as vectors. So it's a bunch of vectors. In order to call this set of vectors, this group of vectors, a vector space, those set should satisfy two major conditions. The additivity of any of two vectors, it will result in a vector belongs to this set. And of course, the addition, it means the 5 properties that you saw. Okay, scaling, which means multiplying any vector by a number, the result will be a vector belongs to this set. Under those remaining other 5 conditions. Those are the 10 conditions. Remark. If a set of vectors and operations satisfy all of these 10 rules, it is a vector space. A failure in any of these 10 propositions, it means it's not a vector space. It's just a collection of vectors or collection of objects satisfying certain conditions. Okay, I believe we need an example to show what we mean. Let's study this. This case is stating the set of all ordered real pairs of real numbers. I'm talking about R2, which is a vector space, R2. What's R2? It's all the set of numbers that belongs to the plan, X and Y, okay? Wait, X and Y belongs to R. So that's the set that I want to show, or that's the set of vectors that I want to check if they are vector space or not vector space. Remark that X and Y belongs to what? To R. What we mean, so what we mean about X and Y belongs to R? It means X can take any value belongs to the set of real numbers. So it can positive numbers, negative numbers, and so on. And 0, of course. Y same way like. The form will be X and Y. Okay? So this means the vectors like اللي مكتوب ده معناه. This means those are the vectors 2, 3, 0, negative 1, pi and 5, 5 and pi, negative 1 and 0, 4 and 100, 1000 and negative 10,000, whatever. It's 2 numbers. Okay. Does it represent a vector space? Is this a vector space? Let's check. If I have any 2 vectors and they added them together, that's vectors x1, y1, x2, y2. If I added them together, the result will be x1 plus x2, y1 plus y2, which is on the same shape. Okay? So the result will belong to the real set. If I have 2 and 3 and 4 and 1, added them together, it will lead to 6 and 4, which is a vector from the same dimension. So it is done for the addition property. Step number 1. Okay, step number 2. Scalar multiplication. If I have a constant and multiplied by any of these vectors, the result will be a vector on the same shape. So multiplying a type of x or y, it will lead to ax, ay, which also contains set of real numbers in the x and in the y, or in the first coordinate and in the second coordinate. An example, it's like 3 times 2 is 3. It will result into 6 and 9 and still belongs to x and y. That means these 2 conditions here already exist. Of course, if I have 3 of them, I can do the same. All the 10 properties is applicable. Also, the existence of the origin, 0 and 0, it belongs to this set of numbers. So it simply represents a vector space. Add 2 vectors, still in R2. Multiplying by any real number, still in R2. Okay, there is a 0 vector, still no. Any vector, it has its inverse already exists. So 2 and 3, it's a vector. Negative 2 and negative 3 belongs to the set of x and y. So it's a vector space. So this is a vector space. Okay? Okay, done. Represent a vector space of R. Okay, let's go to this example. The second example. Miss Fatima, The second example, it is the set of vectors under the condition. It is the set of vectors of x and y, where both x and y belongs to r squared, but satisfying the condition that x plus y should equal to positive 1. So I'm talking about the set of vectors which have how many coordinates? 2 coordinates. Once you add these 2 coordinates together, the result will be positive 1. It's like -4 and 5. When you add them together, the result will be 1. It's like 0 and 1. Once you add them, the result will be 1. It's like half and the half. Once you add them together, the result will be 1. That's the condition. Okay, so the vectors contains, or V contains a set of vectors like 0, 1. Add them together, it will be a 1. 1 and 0, add them together, it will be 1. 2 and -1, it will be 1. 5 and -4, add them together, it will be 1. All those vectors. Does this set or this set of vectors, does it form a vector space? Let's check. If I have any other 2 vectors and added them together, is it going to be satisfied? I believe we will have a failure in the additivity. This is 0, 1, which their addition is equal to 1. And the 1 and 0, their addition is equal to 1. Add them together. So that's a vector belongs to this set. And that's another vector belongs to this set. If I added them together, is the result going to be a vector belongs to this set? Let's check. Add them together. 0 plus 1. For the second component, 1 plus 0 is, their addition is equal to 2. So this condition is broken. So that's a failure. 1 plus 1 is equal to 2, doesn't equal to 1. Which means this is not a vector space. Another issue, does it contain an origin for this set of vectors, which is x and y, with me, Solai? If I'm under the condition that x plus y is equal to 1, do you have an origin? 0 and 0? No. Because if you have 0 and 0, their addition will be 0, not equal to 1. So all the conditions related to the additivity process is not valid. So this is just a collection of vectors, but not vector space. Okay? معايا فريق? Okay, very good. Okay, because it fails just one rule, V is not a vector space. طبعا هنا بيقول لك to be a vector space, it must satisfy all 10 vector spaces axioms. So a failure to do so, this is not a vector space. Okay, let's go to this set. This set of vectors. It is the set of vectors. It's still an R2, okay? But satisfying the condition that both x and y are greater than or equal to what? So I'm talking about the first quarter. Now x and y, it's the x-axis and the y-axis. So you're talking about 4 quarters. Once you have x greater than 0 and y is equal than 0, so I'm talking the vectors that already exist in the first quadrant. Okay, let's check. First of all, if I have a vector belongs to this one, which is 1 and 0, if I have 0 and 1 and added them together, I will have 1 and 1, which really exists in this part. If I have the vector 2 and 3 and 4 and 1, if you add them together, you will end up having a vector which belongs to this set. Since you are talking about x and y greater than or equal to 0, it means the origin already exists. So for the addition, it's already fine. Let's check the multiplication by scalar. If I have the vector 1 and 1, and I'm multiplying it by 2, the result will be 2 and 2, which still belongs to the first quadrant. But if I have 1 and 1, Miss Sulay, and I multiply it by -1, the result will be -1 and -1, which doesn't belong to the first quadrant, which means a failure in the multiplication by scalar. So it's not going to be a vector space. So once more, okay, if we add 2 vectors with non-negativity components, the result will be non-negative non-negativity components and solve the closure under addition. But if you try scalar multiplication by a negative positive value, it will belong to the first quadrant. But multiplying of a less than 0, which means a negative value, you will be talking about elements in the third quadrant, not in the first quadrant. Okay? So it's a failure in the multiplication by a scalar. This is why Mr. Faisal, it doesn't represent a vector space. Tamam? I'm going to say that in Arabic. Okay? For a vector space. I'm going to say it in English, then I will repeat it in Arabic. Okay? In vector space. To be a vector space, it's a collection of vectors. Has a general form. But this general form must satisfy how many main two rules? Two. Additivity rule and the multiplication in a scalar. The additivity rule by itself, it contains 5 things to check. The commutativity, the distributivity, the existence of an origin, and so on. Okay, for the multiplication by scalar, it contains by itself 5 components. Multiplying by a positive number, by the distributive, on scalars, and so on. A failure in any of these, it will make it just a set, but not representing a vector space. Okay. Very good. انت عندك 10 حاجات لازم تتاكد منهم. مني حاجتين. المجموع بتاع اي 2 فيكتور يبقى بينتموا لنفس المجموعه، او لو انت عندك فيكتور ضربته في رقم لازم الريزلت تنتمي لنفس المجموعه. اوكي؟ كل واحد من الكونديشنز دول فيه 5 بارتس، التوزيع والتبديل وخلافه. فيلير في اي واحد فيهم خلاص it's not a vector space. Okay, done. So V is not a closed under scalar multiplication, so it's not going to represent a vector space. Also R3, X, Y, and Z, X, Y, and Z. Those 3 coordinates, they represent a vector space. Because if you have a vector in 3 components and add it on a vector of 3 components, the result will be a vector in 3 components, which is still a vector space. Once we talk about R3, you will have the origin, which is 0, 0, 0, which an existence of the 0 condition. If I have a vector in 3 dimension, which contains 3 components, and I've multiplied them in a constant number, I still will have 3 components. So the multiplication and the addition is already satisfied. Okay, once more, as I told you, x1, y1, z1 plus x2, y2, z2, it will result in x1 plus x2, xy1, which is 3 components. We are very good for the addition. The multiplication by scalar will be the same, 3 components. The existence of a 0, the existence of a negative value, it's all exist. So it represents everything. It contains a 0, the existence of the opposite values, the existence of the identity. So it's a vector space. Okay. Once more, attention, please. Remark, vector spaces, once more, that's the main definition. A vector space is non-empty set. It's a set, non-empty. So if I told you the vector space 0, 0, 0, does it represent a vector space? No. Why? Because it's non-empty set. Okay? So a vector space V is a non-empty set whose elements are called vectors, in which there are defined 2 main operations: addition and multiplication by a scalar. So for every UVW, for every 3 vectors belongs to V, and for every A and B belongs to R, then you will have the following: the addition, the distributivity, the commutativity, the addition of a 0 that exists, the addition of the inverse of the numbers, the multiplication by scalar, the distribution on 2 numbers, the distribution on the constant number on 2 vectors, distribution of 2 scalar values in U and V, and the existence of 1. These are the 10 conditions that should be satisfied for anything to be a vector space. Okay, examples. R represent a vector space. The set of real numbers, the set of real numbers, think the set of real numbers, 1, 2, 3, 4, 5, 6, negative 1, negative 2, and so on. And their fractions represent a vector space. Why? Because each one of these numbers, if you added, multiplied, or whatever, you will find it on the real number. And also contains the zero. And also contains the inverse of each of one of these numbers. So it represents a vector space. R2, of course, and we already checked that, it represents a vector space. R3, similarly like, which represent, that's an X, that's a Y, that's the Z. Okay? Also 3 dimension, and it represents a vector space. I can write them as R2, which is the set of all X and Y, such that X and Y belongs to R. Also R3 can be represented as the set of elements X, Y, and Z, such that X, Y, and Z belongs to R. This is the way I can write a vector space. Are you with me, Sulay? Okay, not just only the vectors, but I have a lot of things. For example, for R5, R5 is gonna the set of vectors, which is represented by how many components? 5 components, and all the 5 components belongs to R, and you will find all the conditions to release this one. Also, the set of matrices of 2 and 3, they represent, listen, the set of matrices of dimension 2 and 3, they represent by themselves a vector space. Why? Because if I have a 2 by 3 matrix, it's not going to be added or subtracted unless from a matrix 2 by 3. And the result will be 2 by 3. So the additions exist. If I have 2 by 3 matrix and multiplied it by a number, the result also will be a matrix 2 by 3 and still belongs to the set of 2 by 3. One of the matrices in 2 by 3 is the null matrix from the dimension 2 by 3, 2 rows, 3 columns. So it's a matrix with all elements equal to 0. And it's displaying the identity of addition and subtraction. Are you with me, Farid? So the set of all matrices, okay? The set of all matrices of the dimension 2 and 3 also represent a vector space. تمام يا شباب؟ طيب, a set of all matrices n by n, it represents the set of matrices a vector space. Okay, and so on. قولي لي. لا, 2 by 3 is a set vector space. 2 by 2 is a set vector space. 5 by 2 is a set of vector space. They form a vector space. لأن أنا لما بتكلم على 5 by 2, I'm talking about all the matrices with the dimension 5 by 2 with all elements. The major 3 things that we usually check: additivity, multiplication by a number, and the existence of origin. And the 3 are satisfied. Are you with me? Perfect. Vector space example. This is Rn, خلاص, we already done. M by n matrices, it's already done. The set of diagonal matrices, the set of upper triangular matrices, the set of lower triangular matrices, they are all vector spaces. Each one of them is a vector space. Okay? All the conditions, the 10 conditions are satisfied. Proposition. Let V be a vector space. Then, for each vector, its symmetric is unique. And it is already exists. If I have the vector 1, 1, 1, its inverse, which is -1, -1, it's unique. If you are talking about the multiplication inverse, so the vector 2, 2, 2, there is a unique vector that will be the multiplicative inverse, which is half, 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 and so on. So the existence of a symmetric unit is unique. A times 0 is equal to 0, 0 times V belongs 0. The 0 in any of the vectors, it will result in the origin of this vector space. A times the 0 vector of a vector space will decide to 0. -1 times V is going to be negative V. A times V is equal to 0 to the 0 or the null vector. It means A is equal to 0, or implies A is equal to 0. I'm going to talk now about the sub-vector spaces. Each vector space, it may have more than one sub-vector space. The sub-vector space is a subset from a vector space. But, of course, as it is a sub-vector space, so the major 2 operations must exist, which is the additivity and the multiplication of the square. But it has to have the same origin. So if a vector space, just Just I usually see it like this. If I have this set is a vector space, if this is a vector space, and that's the origin of this vector space, so each circle inside the bigger one, that's a sub-vector space from this vector space. But this set, it is not a sub-vector space. Because the origin of this set is not the origin of the major vector space. Are you with me? So to have a sub-vector space from a vector space, they should share the same origin. You have to put this into mind, okay? I will go through the details. Of course, every vector space is a sub-vector space from itself. Once more, every vector space is a sub-vector space from itself. Okay, once more, W is said to be a vector space of W is said to be a vector subspace of VF. Number one, 0 belongs to W, so 0 now belongs to V and the W. Or the 0 of V, the origin of V, belongs to W. Number two, U plus V belongs to W. If you have vectors belongs to W, their summation should also exist in there. And the multiplication by scalar. If you have a vector that belongs to W, if you multiply by a number, it should exist within the set of these elements of the W. A vector subspace of a vector space is a vector space by itself. Okay, a vector subspace, okay, of a bigger vector space. This vector subspace by itself, it's a vector space for its elements because it satisfies the main conditions, the additivity and the multiplication by scalar, and so on. How can we revise a vector to be a subspace of another vector? ازاي اقدر اعرف ده؟ بكل بساطة زي دي مثلا. Let's look to this example. Okay, V is the set of all vectors of the form A and 0. All vectors of A and 0 is like the vectors or the components of the x-axis. Because A belongs to R. عارف زي ما نحط to the pair or the coordinates, the ordered pairs that exist on the x-axis. ما هو ده A و0. هيبقى 1 و0 2 0 3 0 negative 1 و0 negative 2 0. Okay, وهكذا في البوزيتيف والنيجاتيف. Are you with me? Okay. They have an x component, but they share that the y component is equal to 0. So this set of vectors, okay, belongs to the x-axis. They represent a vector space. Okay, any two vectors, A and 0, if you add it on another vector, B and 0, the result will be a vector will exist. And the origin already exists, 0 and 0. So it is a vector space. Okay? Does this set of numbers is a subset from R2? Is it a subset from R2? Yes, I will show that. They share the same origin. The origin for R2 is 0 and 0. And they share it with A and 0. So the origin already exists. Okay? Any two vectors belongs to R2. If you add them, you will have two components. So we already proved that R2 is a vector space. So it is already a sub-vector space. Number one, the origin already exists when A is equal to 0. If A is equal to 0, you will have the origin. Number two, A0, B0, the result will be A plus B and 0, which belongs to V. The third one, A0, if you multiply by a number, it's lambda, alpha, whatever, the result will be a shape, belongs to the same, so it's a sub-vector space from R2. The three conditions are satisfied, and they are sharing the same origin, so it's going to be a sub-vector space. So V is a sub-vector space of R2. Okay, these also are called vector subspaces. R3 by itself is a sub-vector space from R3. The part 0, 0, 0, this is not null. That's the set of the vectors which contains triple 0. If I have triple 0 multiplied by number, it will be triple 0. If I have triple 0 and added it on a triple 0, the result will be triple 0. So it represents a vector subspace. What I meant by an empty set is just a set that there is nothing inside it, not even the null vector. Are you with me? Every line of R3 passing through the origin, is every line in R3 represent a subvector space to R3? Please think. Is every line in R3 represent a subvector space from R3? No. Why? Because every line doesn't mean necessarily to pass through the origin. And you have a condition to be a subvector space from a vector space that they should share the origin. So you can have lines already in R3 but not passing through the origin. To make the lines form a subvector space from R3, I will talk about just only the lines that pass through the origin. So he's stating every line of R3, but under the condition Yazid, if you're passing through the origin, represent the subvector space from R3. Okay, every plan of R3, every plan of R3, but under the condition that it passes through the origin, it's also a subvector space. This can be given to you, or you can ask it about this, Ya Jama, as a statement. As I told you, and as we saw previously in the previous exams, he will always ask you, define or find the right statement from each of the following. And he will give you more one statement, and you will see which is right to choose. Are you with me? Okay, perfect. Okay, is that A and the A plus 1, whoever A belongs to R, represent the vector space of R2? I need you to think. Nada. I'm talking about the set of vectors which contain two components. Just two components, satisfying that this is A and the A plus 1. It's like 0 and 1, 1 and 2, 2 and 3, okay? 1, 2 and the negative 1. I'm sorry, negative 2 and the positive 1. Negative 2 and positive 1. This condition should be satisfied.